Okay, now we'll talk about alternating series and absolute and conditional convergence. So let's start by looking at these three sequences first. These are not series, these are sequences. Let's write out a couple terms of these things. So when n equals 1, an becomes -1. N equals 2, you get +1. N equals 3, -1, +1, so on. Same thing here for Bn. We're going to start with n equals 1. We get +1, then -1, +1, -1, so on. And then looking at cosine of n pi, starting with n equals 1, we get -1. Cosine of pi is -1. And then cosine 2 pi is 1. Cosine of 3 pi, -1. Cosine 4 pi, 1, and so on. So what happens is you're going to start seeing series that contain some kind of alternating part like this. So it might look something like -1 to the n over n plus 1. This would be an alternating series. This -1 to the n is going to change the sign of your series over and over. That's what makes it alternating. So when we have a few definitions of convergence for alternating series, but we're going to see how these apply first. So the way you test for alternating series for convergence is you test first if it's absolutely convergent. We'll write a little flowchart here. So first you're going to check if the series of the absolute value of your sequence converges. If it does, then you say series is absolutely convergent. This implies that the original series, not having the absolute value, is convergent. If the absolute value of your series does not converge, you check series using the Leibniz Criteria. If it satisfies this, then you say series is conditionally convergent. If it does not, you say it diverges. So, to summarize that again, you're going to start with an alternating series. You're going to take the absolute value of the sequence and consider that series instead. If that converges, then your series converges absolutely and you're done. If it does not, then you check. It doesn't mean that you're divergent. You check the series using the Leibniz Criteria. After that, if the series converges, then you say it converges conditionally. If it doesn't, then it diverges. So we'll look at a few examples of this. Let's look at an example. Negative 1 to the n to the 1/3. Okay, so we see this negative 1 to the n expression showing up. That means that this is an alternating series. So we will test for absolute convergence by instead considering the series equals 1 to infinity, the absolute value of this thing. So when we take the absolute value, what ends up happening is the alternating part disappears and you're just dealing with this function now instead. This series, excuse me. Now, what does this series do? Well, this diverges because it's a p-series with p less than 1. So right now we are saying that this series diverges, but it doesn't mean that our original problem diverges. Our original problem can still converge conditionally. So we're going to apply the Leibniz Criteria to test for conditional convergence. So 3 things we have to show. The sequence an, and the an is a part, it's basically everything that's not alternating. So 1 over n to the 3rd would be our an. The sequence has to be positive. 2 has to be decreasing. And 3, the limit as n goes to infinity of an has to be equal to 0. If it satisfies all 3 of these, we say it converges conditionally. So let's look at our problem. Not negative, just 1 over n to the 3rd. Okay, so clearly this is positive for all n between 1 and infinity. This is always positive. So that takes care of the first check. That's the second one. It has to be decreasing, so we'll take the derivative. We take the derivative of the corresponding function, but it's the same thing, so 1 over, we'll rewrite it as x to the negative 1/3. And the derivative of this is negative 1/3 x to the negative 4/3. So this, of course, is equal to negative 1 over 3 times the cube root of x to the 4th. So this number here is always positive. This is always positive because it's the 4th, and we've got a negative in front. So this derivative is always negative, which means our function is decreasing. And 3, the limit as n goes to infinity of 1 over n to the third. Well, this is, of course, 0. So what does this mean? Our series, n equals 1 to infinity, our original problem, negative 1 to the n, divided by n to the 1/3, converges conditionally. Let's look at another example. Okay, so we see an alternating portion again. So we're going to take the absolute value. And when we take the absolute value of this thing, we're just going to end up with 1 over 1 plus 1 over n. And this is the series that we're going to consider instead. So let's just try the divergence test on this thing. So the divergence test says take the limit as n goes to infinity of the sequence, 1 over 1 plus 1 over n. And you can see that this goes to 1. So if the divergence test yields a number other than 1, then the series diverges. So this implies series diverges. So our series does not converge absolutely, but it could still converge conditionally. So we will test using the Leibniz Criteria. I don't know how to pronounce that word. I'm going to keep butchering it. So 1, are the terms positive? Oh yeah, 1 over 1 plus 1 over n. This is clearly always positive numbers on this interval 2 to infinity. So that's true at least. Second criteria, is this function decreasing? Well, that's a good question. So we might want to rewrite this a bit. Multiply through by n over n. So we'll get n over n plus 1. And when we take the derivative of the corresponding function, we're going to get, using the quotient rule, x plus 1 times the derivative of the top, which is 1, minus top times derivative of the bottom, which is 1, divided by the bottom squared. So this is equal to x plus 1 minus x all over x plus 1 squared, which is equal to 1 over x plus 1 squared, which is not decreasing necessarily. Well, it's not always decreasing. So it doesn't satisfy the criteria, so this series diverges. It didn't satisfy absolute convergence, nor did it satisfy conditional convergence. So the series diverges. Let's look at another example. Okay, so this is the third type of alternating term that we had. So again, we'll consider the absolute value of this. And when we do that, we're now only considering this function, 1 over the natural log of n squared. The cosine n pi disappears because it's alternating. So I'll try to figure out if this converges or diverges. Recall that the natural log is the slowest growing function we have, so we can bound it by pretty much anything. We'll say that the natural log of n is at some value of n less than or equal to square root of n, which means the natural log of n squared is less than or equal to n, which means 1 over natural log of n squared is greater than or equal to 1 over n. So this series of 1 over natural log of n squared is greater than or equal to the series n equals to infinity of 1 over n. This is a p-series, a divergent p-series. And our series is bigger than that, so our series diverges. Which means we have to check. Well, that means our original series does not converge absolutely, but it may converge conditionally. So we're going to apply the Leibniz Criteria again to this sequence, 1 over natural log of n squared. Is this positive? Well, yes. Natural log is going to be positive on the interval 2 to infinity, and furthermore, it's something squared, so this is always positive. Number 2, is it decreasing? Well, we'll take the derivative and see. 1 over the natural log of x squared. This is natural log of x to the negative 2. And then now we'll take the derivative. We'll get negative 2. Applying the chain rule. Natural log of x to the negative 3 times 1 over x. Now this isn't quite as obvious, but we're only plugging in positive numbers for x because our interval is from 2 to infinity. So this here will be positive, and the natural log is positive on the interval. So you get a negative times a positive times a positive, and that becomes negative. So it's always decreasing. And then 3, the limit as n goes to infinity of 1 over natural log of n squared. Well, the bottom is the only thing that has n in it, so this is going to go to 0. Therefore, our series converges conditionally.